hopefully I put a title on this, and if I do, it should say something along the lines of acetals, amines, amines, and enamines. Okay. The fact that it's those three is that the mechanisms are very similar between them. There's actually not much difference. Okay. There's a couple things we're going to keep in mind and going to continually ask ourselves throughout these problems. That is, what's the goal? Okay. So what's our long-term goal? What's our product? What should it look like? Either what does that functional group look like, or what does my entire molecule maybe look like, if you're comfortable predicting the products that way. What's the goal? Okay. We can also ask ourselves, also keep in mind acidic versus basic conditions. Okay. And we can also, in this, remember, leaving groups, okay, in this case it's always going to be water. So for acetals, for imines, for enamines, water is always going to leave. Okay, so leaving group there. Let's go ahead and start with acetals. I'm going to go through these, I think, hopefully pretty quick because they're videos. Pause them, try them on your own before, and then you can pause or slow them down as we go through it, when we go through it kind of fast. So I can put them all in one video and actually download the thing. Let's start off with acetals. Acetals can only be performed in acidic conditions, okay? Acetals, acidic conditions, okay? With enamines, we're going to be enamine elimination, EE. With acetals, AA, acetals, acidic. It can only work under highly acidic conditions. Pick your favorite strong acid. Mine is sulfuric acid because that is what the book chooses. Okay. My acetal at the end, okay? A definition of acetal group. I need two ethers on the same carbon, okay? Something that looks like that, okay? All right. In order to make an acetal, I need highly acidic conditions. And I need alcohol, not just alcohol, excess alcohol, okay? My final product, acetal, should have some type of two ethers on it, okay? And for acetals, for imines, for enamines, I need some type of carbonyl carbon. Let's just use a ketone, okay? And I need excess alcohol. That's different than hemiacetals where I just needed alcohol. Now I need excess alcohol. Okay, and for our purpose, let's use methanol. Okay. Awesome. Okay. Now, if you do this enough, you get good at it, you can see that these two reactants should form this acetal, where these are our three carbons of our ketone here, and then I'm adding two ethers with methyl groups on them using my alcohol there. I said I'd go through this fast. I'm not. I gotta speed this up. Highly acidic conditions, I can assume that this is protonated. Assume it's protonated. We're done using H2SO4. We don't need it anymore. That's it. We're only working now with this that's protonated, this when it's not protonated, and our carbonyl. That's it. This protonated, this not protonated, and our carbonyl. It's the only thing that's going to react from now on. Okay, that's it. Even though it might be like 7 steps, we only really have 3 options. Okay. Assume that's protonated. I'm going to activate my carbonyl group. Under highly acidic conditions, that's always gonna happen. Activation, carbonyl group, proton transfer, I'm left with this protonated, okay? I have an option. I now have a really active site here, my carbonyl group that I want to attack. So I can either use methanol or I can use protonated methanol. What's going to be a better nucleophile to attack? Methanol, okay? Nucleophiles with a positive charge, not good, okay? Nucleophiles with a neutral charge, better, okay? So I only had an option, methanol or protonated methanol. What's going to attack? Just methanol. Okay, move those up. Because these are reversible, I'm going to be using double-sided arrows throughout my entire mechanism. Okay. Bump that up, and I attached that there. Charge. I have a positive charge. I want to deprotonate. So am I going to use methanol or am I going to use protonated methanol? I'm just going to use methanol to deprotonate. Okay. Okay. Cool. I've eliminated my charges. I'm done. Almost, okay? This is a hemiacetal, so I got to keep going. I need to add another alcohol on there, aka I need another carbonyl, and we'll get used to water leaving, okay? So in all these examples, and I write them the same way so we can see this, we see an alcohol here, it's going to leave. Just get used to that. Just get used to that, okay? Unless I'm making just an acetal, I'd be done. It's okay. This is what I expect. Because I need to put another ether on there, I need water to leave, okay? So, alcohol is a bad leaving group. I need to protonate it to get to water. I need a proton. Should I use methanol or protonated methanol? I should use protonated methanol because I need a proton. Okay, proton transfer again. I now have water. Water can't just leave by itself. Your textbook says that. I would not follow that. It's going to help us out in the long run if we do it the more correct way, the way Dr. Andrews prefers it as well. Okay, water is just not going to leave. Okay, we need something to kick it off. Again, in acetals and imines and in enamines, all these are going to be the same up to this point. Reform the double bond to kick water off. We made water so it could leave. Let's kick it off. Reform the double bond. Water leaves. Okay. Left with this positive charge there. Okay. And I had water leave. Okay. I have a carbonyl. Not only that, I have an activated carbonyl. What do we do when we see a carbonyl? Attack, okay? We attack. Same thing here. We need to add another methyl group on, okay? Am I going to use methanol or protonated methanol to attack? I'm just going to use methanol. It's a better nucleophile. Attacking my carbonyl, push those up onto oxygen. Here's oxygen I pushed up. Here's my new group. I'm really close to being done. You can see I'm only one hydrogen away from my final product I predicted at the beginning. I need to take a proton off. Am I going to use methanol or protonated methanol? I'll be saying that a lot, okay? I need to take a proton off. Let me use deprotonated methanol, just regular methanol, okay? I need to take a proton off. I'm just going to use regular methanol. Take that proton off, okay, and move that bond onto oxygen. I'll be left with my final product. Right. Here's my acetal. Okay. All right, let's move on. It's going to be extremely similar. We're going to make imines. Okay. Acetals and imines don't look much like each other. The reactions are basically the same. That's why they're all going in the same video. Because the reactions are pretty much the same. Okay. For imines. Definition of an imine, in my final product, I should expect somewhere to be that. Carbon double bonded to a nitrogen. Okay? I should expect that in my product. What's the goal? Right there. My leaving groups, what are my conditions? Nitriles can only, not nitriles, imines can only function, okay? Again, we need some type of carbonyl to again use a ketone. Okay. Now, with an acetal, I needed, for example, I needed excess alcohol. For imines, I need either ammonia, NH3, okay, or NH2 as a primary amine. Let's put an R group on there, okay? NH4, too many protons, not a good nucleophile. Secondary, or if I do a secondary amine, we'll see that we actually make an enamine. So these are my two options, either NH3 or NH2 with some type of carbon chain on it. For our example, let's just use a primary amine. Okay? And when we're making imines, we use mildly acidic conditions. And that's all the further we need to go for that. Hemiacetals, acidic or basic. Acetals, acidic. Remember, acetals acidic. Acetals acidic. Imines, somewhere in between, mildly acidic. Okay? And we put that down, we don't need to worry about it. All that can react is our carbonyl, either our ammonia or our primary amine, and its protonated version. It's the same as when we were dealing with just methanol. It was either, every time, was it methanol or was it protonated methanol? Okay, same thing here. Is it the protonated version? Is it the deprotonated version? Let's go ahead and work this out. I'm not highly acidic, so the first thing I'm going to do, I'm not going to activate that carbonyl. That's only if it's highly acidic. I just go straight up. I have a carbonyl I can attack. I have a pretty good nucleophile. I don't need to protonate anything off the start. Okay, first step there. Doesn't really matter which charge I don't think we address first. Your textbook goes with negative charge, so we're going to stay consistent with that. I want a proton to protonate my oxygen. I want to get rid of these charges. I want to protonate oxygen, so I use the protonated version of my primary amine. I want a proton. NH3 now, with a proton on there. Proton transfer. Okay. Okay. NH2, okay. I want to take a proton off to get rid of the positive charge, so I should use the deprotonated version of my primary amine. I want to take a proton off, so let me use my deprotonated version. Okay. proton transfer. All right. 1, 2, 3, 4 carbons. 1, 2, always count my carbons. I missed one there. Okay. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Cool. All right. I'm kind of stuck here. I ran out of charges. What do I do? If you notice, at this point, it's at the same point. Okay. Water. Water's going to leave. Okay. Acetals, imines, enamines. Water's going to leave. Okay. I got rid of my charges. I'm kind of stuck here. What do I do next? Water leaves. Okay. It's alcohol right now. We have to protonate it. We need to protonate something. I want to use the protonated version of my primary amine. NH3. Okay. Make this water. Just like before in acetals, water can't leave just by itself, okay? So we need to kick it off. We reform the double bond to do that. One pair of nitrogen, reform the double bond. We made water so it could leave. So let's do that. There's the nitrogen double bond. There's its 2 carbons. What was our goal to start out with? Let's go back. We want a C double bond to an N. We've just made that, okay? Having water leave by itself, we have to do a resonance structure to get here. So I think it's better if we initiate that to kick off water, because then we're left with the resonance structure that's easier to work with, okay? We get the structure here, we want to take a proton off, and then when we'll be done, we want to take a proton off. Let me use a deprotonated version to do that of our primary amine, NH2, proton transfer, electrons go on to nitrogen. I'm left with, I'm going to draw that down here. Proton transfer. And there is our amine. Okay. Awesome. Okay. Still recording. All right. So yeah, it's really the same steps as before, only we didn't protonate at the beginning. So amines and acetals are pretty much the same, only one's under highly acidic conditions, one's under mild conditions, okay? Identifying what our final product should have, or what maybe it entirely looks like, should help us move forward if we ever get stuck. And remember, water is going to leave in these 3, acetals, amines, enamines, okay? Last ones, we'll do enamines, and we'll see there's a lot of repetition. A lot of repetition. So enamines, nitrogen, and then a carbon-carbon double bond, okay, 1 away. We should expect this structure in our final product, okay? Again, we need some type of carbonyl. We'll use a ketone. Remember with amines, it was NH3, primary amines. To get an enamine, we need secondary amines, okay? So we're continually being more oxidized, I guess. Less reduced might actually be a better term here. NH3 and NH2, okay? Those were amines. Just NH with 2 R groups, aka a secondary amine, like that. Okay, this is going to make our enamine. Okay, NH3 and our primary amines Those were imines to make imines, what we just did. This is now to make an enamine. So we need some type of secondary nitrogen group, okay? That could even be something like that, secondary amine. We won't use that because we don't need to be carrying a ring around the entire equation, entire mechanism. So we'll do something just like that. Diethylamine, I think. Okay? And again, we need mildly acidic conditions. A lot of these are going to be review. Okay? Try it on your own. See if you can go all the way. I'm not highly acidic, so I'm not going to protonate anything first. I'm going to attack straight away. Those electrons go up onto oxygen. Oxygen gets a negative charge. Nitrogen attacks. It has two ethyl groups on it. A hydrogen, it gets a positive charge. I want a proton. Let me use the negative charge there. I want a proton there. Let me use the protonated version of my secondary amine, okay? That's going to look like, okay, group there. Anyway, okay, I need a proton. I'm going to use my protonated version of my secondary amine. Protonate. Okay. This is protonated now. I want to take a proton off. Okay. I want to take a proton off of this nitrogen here. Let me use the deprotonated version. It'll accept a proton. Deprotonated version. Goes on to nitrogen. OH group. Nitrogen and my two ethyl groups. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. I screwed up somewhere. Right there. Right there. Okay. You see I miss carbons sometimes too. Always a good way to check. My starting material, 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. Okay? Same as before. I've neutralized the charge. What do we notice is the same? Water's got to leave. Okay, right now it's alcohol. We need to protonate it. What should I use? The protonated version of my secondary amine. Protonate it. Becomes water. Okay? I've made water so it could leave. How do I initiate water leaving? Okay, I need to kick it off, reform the double bond. Reform the double bond and have water leave. One, two, three, 4, 5, 6, 7, 8. Where did I screw up here? Okay, there we didn't lose any carbons or gain any. Kind of neat looking, okay? Now I can't just deethylate, okay, one of these groups off. But if you notice, okay, this is the same steps as before in both acetal and in amines. Same as before. I get to this point, I can't just take an ethyl group off. The next two steps, this is the only thing that's going to change between the three of these, okay? Our acetals, our amines, our enamines. Resonance here and elimination. Enamine elimination, okay? Resonance here, and then we'll do an elimination reaction and we'll be done. Resonance here. Remember, resonance is just moving, okay? Make double bonds into lone pairs and lone pairs into double bonds. Where can I move a lone pair here? Oh, I can move it onto nitrogen. That way, nitrogen's making 3 bonds and has a lone pair, okay? It's a reasonable resonance structure. There's the lone pair, and I have a carbocation down here. Here's my resonance structure. I got to this point, resonance and then elimination, I'll be done. Elimination reaction, beta proton, not a beta proton, alpha proton, okay? And I make a double bond, okay? Just like an E1 reaction, okay? Elimination. Bases are proton acceptors, okay? I'm gonna use this structure here. I use my resonance to get right here. I'm 1 step away. I'm gonna use the basic version, okay? I just need to take an alpha proton off. So I'm accepting a proton. What am I gonna use? Am I gonna use the protonated version or the deprotonated version? I'm gonna use the deprotonated version. My secondary amine, I'm going to deprotonate an alpha hydrogen and form a double bond right there. And notice that will give me my double bond there. My enamine product, okay? 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. I've made a nitrogen. I've made one away from a double bond, so I made an enamine there. Predicted an enamine, I made an enamine at the end, okay? Acetals and imines, really the same thing. Only one's under acidic, acetal acidic, protonate to begin with. Imines, straight nucleophilic attack, same steps as acetal. And then with our enamines, same as imines and acetals really. And the only thing we had to remember at the end, resonance, elimination. Okay.